Hello everyone. Today we are going to see into our refrigeration and air conditioning lecture series how to solve the problems on the air refrigeration system or air cooling system. Okay. So for that I have taken a problem from the Mumbai University examination. So this is the question paper of a third year mechanical same 6 choice base dated 12 December 2019. So here we have taking a question problem as question number 2b. The following data refers to a simple aircraft refrigeration system. The RAM air temperature and pressure 30 degrees Celsius and 1 atmosphere. Cabin air temperature and pressure 27 degrees Celsius and 1 atmosphere. Pressure at the exit of main compressor 4.5 bar. Effectiveness is equal to epsilon of heat exchanger effectiveness cooling. Heat exchanger effectiveness cooling, it is zero point 0.8. Efficiency of compressor is 0.84. Efficiency of expansion, that means turbine efficiency, is 0.8. Load is 21 kilowatt. From that we have to determine first tonnage, second mass of air blade from main compressor for refrigeration, heat rejection, power, COP, and power required for the blower. Okay, so this is the problem for simple aircraft refrigeration system. So we have already seen what is the simple aircraft refrigeration system. Okay, I will see. So from the simple aircraft refrigeration system, so we will draw the TS diagram for simple aircraft refrigeration system. So in that, in the problem we have directly given as temperature T1, that means ram air and pressure. So that means T1 we will consider the point as ram air input to the compressor. So one number point indicated as a ram air. Okay. So corresponding temperature is 303 Kelvin and pressure is 1 atmosphere, that is 1.01325 bar. Okay. Then we have given 27 degrees Celsius and cabin temperature and pressure as 1 atmosphere, and the temperature is 27 degrees Celsius, that means 300 Kelvin. Okay. Now, so one number point is indicated as a ram air. That air is the input to the main compressor. So that's why 1 to 2 is indicated compression process, main compression process. So 1 to 2 dash is a isentropic compression process. 2 to 3 is a heat exchange between the heat exchanger, and 3 to 4 is the actual turbine expansion, or the air will be expanded on the turbine. 3 to 4 dash is the isentropic uh, air expansion on the turbine, and the point number 5 indicated as a cabin air and pressure, that means point number is for cabin pressure. Okay, so from the given data we have written down T1 as a 303 Kelvin, that means ram temperature. Ram pressure is 1 atmosphere. P2 is equal to P3, that means expansion is cooling is taking place into the heat exchanger. 2 point is indicated as a compressor outlet, 3 is a heat exchanger outlet. So pressure in the heat exchanging process is the same, so that's why P2 is equal to P3 is equal to 4.5 R. Effectiveness of heat exchanger is 0.8. Then cabin temperature, as we have given 300 Kelvin, and pressure is 1 atmosphere, that's why P5 is equal to 1 atmosphere. Efficiency of compressor is 0.84, and efficiency of expansion, that means turbine efficiency, is 0.8, is 80%. And we have given the load as 21 kilowatt. We have to find out first Q, that means load in the tons of refrigeration. Second, mass flow rate of air. Third, the heat rejection into the uh, heat exchanger process, and then power and COP of the turbine. Okay, sorry, COP of the refrigeration system. So now we'll see one by one solution process as so here. So total turner load we have given in terms of 21 kilowatt. So Q total load is equal to 21 kilowatt is equal to 21 divided by 3.5. So 1 ton of refrigeration is equal to 3.5 kilowatt. So we'll divide this value. So we will get the 6 tons of refrigeration is the value for the load capacity. Then now we will solve for the mass flow rate of air. So one by one we will see here for the process compression process 1 to 2 dash. This is isentropic process. So first we need to find out the temperature corresponding to 2 dash point. So here according to the isentropic relations, so we have T2 dash divided by T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma. So from that we have found out T2 dash is equal to 303 multiplied with 4.5 is P2 pressure and 1 atmospheric pressure is 1.03251 raised to gamma is value index of air. This is gamma is 1.4. So 1.4 minus 1 is 0.4 divided by it is 1.4 divided by gamma is 1.4. After solving this we will get in the temperature of the isentropic compression outlet. So this T2 dash is equal to 463.92 Kelvin. Now by using efficiency of turbine we'll write down the formula. So maximum, if you see here, ideal divided by actual. So this is the efficiency of compressor 1. So for that, so ideal is T2 dash minus T1 divided by actual is T2 minus T1. So T2 minus T1. So 1 to 2 process is actual compression process and ideal compression process is 1 to 2 dash. So this is so compressor efficiency we have given T2 dash minus T1 divided by T2 minus T1. So this is in the terms of temperature ratio. So after substituting the values, compressor efficiency is 0.84 is equal to 463.92 minus 303 divided by T2 minus T1. So we will find out the actual compressor outlet temperature. So this temperature is 494.57 kilowatt. Okay, so this is the point number 2 temperature. Okay, now next one. So second process is we have the heat exchanger process and we have provided the effectiveness of heat exchanger. This is equal to how much heat is rejected divided by how much heat is added into the air. So heat is added into the compression process and heat is removed from the air from the heat exchanger process. So effectiveness is equal to T2 minus T3 divided by T2 minus T1. So corresponding temperature. So this is 2 to 3 is a cooling process and 1 to 2 is heat addition, that means during the compression process. So from that here we find out 0.8 effectiveness of heat exchanger is equal to 494.57 minus T3 temperature divided by 494.57 minus 303 temperature. So from that we will find out the temperature as T3 is equal to 341.31 Kelvin. Okay, so we will reach up to the point number 3. Now we will go for expansion process. So for again expansion process, if you see during the expansion process here 3 to 4 dash point is a ideal expansion process, that means isentropic process. From that we can find out the temperature and pressure corresponding to 4 dash point. So we have already provided the pressure as the same as cabin pressure, so that's why P5 is equal to P4 dash or P5 is equal to P4. Okay, so we know the pressure, but we need to find out the temperature corresponding to 4 dash. So for that we will use the isentropic relation as same as compression process. We have already seen T3 divided by T4 dash is equal to P3 divided by P4 raised to gamma minus 1 upon gamma, because same air is expanding into the turbine. So that's why gamma minus 1, gamma is the index of air. So that's why, so we will substitute here the values of T3 So T3 is T4 341.31 divided by T4 dash is equal to pressure ratio as 4.5 divided by 1.01325 gamma raised to 0.4 divided by 1.4. So gamma is 1.4, 1.4 minus 1 is 0.4, and gamma is as it is 1.4. If we solve this, we will see here the temperature for T4 dash as here 222.92 Kelvin. Okay, now we need to find out the actual turbine outlet pressure and temperature. Pressure is known, but we need to find out the temperature corresponding to point number 4. So for that we will use the efficiency formula of the turbine. So turbine efficiency formula is equal to actual process divided by ideal process. So actual process is T3 minus T4 divided by T3 minus T4 dash. Okay, this is equal to 0.8 is the efficiency of turbine. We will substitute the values of T3 and T4 dash. So 341.31 minus T4 divided by 341.31 minus T4 dash temperature 222.92 Kelvin. After solving this, we will see the temperature at corresponding point number 4 is equal to 246.6 Kelvin. Okay, now from the mass fluid of air formula, we will find out the mass fluid of air. So what is the formula of mass fluid of air? Is equal to m dot a is indicated mass fluid of air is equal to 210 q divided by cp multiplied with the temperature difference T5 minus T4. So this is the temperature difference from the cabin to the input to the cabin. Okay, so here we have 210 multiplied with 6. So 6 is the load in tons of refrigeration divided by Cp is 1.004 in bracket T5 temperature 300 minus T4 temperature 246.6 Kelvin. Okay. Now after solving this, we will get mass flow rate of air is equal to 23.50 kg per minute. So this is directly we are getting in kg per minute. Okay. Now next point, we need to find out the heat rejection. Okay, heat is rejected in the expansion heat exchanger process after the compression. So we have the formula heat rejected QR is equal to mass flow of air multiplied Cp of air in bracket temperature difference of compressor outlet minus heat exchanger outlet. Okay, after substituting the values of temperature and mass flow of air and Cp of air, we are getting mass flow of air 23.50 multiply with Cp is 1.004 and T2 temperature is 494.57 minus T3 temperature is 341.31 Kelvin. Okay, after solving this, we are getting heat rejecting as QR is equal to 3616.01 kilojoule per minute. If you convert it into kilowatt, we have 6.267 kilowatt. Okay, so this is about the heat rejection. Now next one, power calculation. So power is we have directly deliver power to the compressor, main compressor. So for that we will require the corresponding pressure temperatures of the compression to find out the power. So we have the power formula is equal to mass flow of air multiplied Cp of air in bracket temperature difference of compressor outlet temperature minus compressor inlet temperature, and we know that the compressor inlet temperature is ram air divided by 60. Okay. So we have after substituting the values, power is equal to 23.5 mass flow of air multiplied with 1.004 Cp of air. T2 temperature is 494.57 minus T1 temperature is 303 Kelvin divided by 60. After solving this, we are getting power as 75.33 kilowatt. Okay. And now fifth point is we have to find out the COP of refrigerant system. COP of refrigerant system, we know that COP means the ratio of heat rejected divided by power delivered to the compressor. So heat is rejected, we know that as tons of refrigeration. So COP is equal to 210 Q divided by power multiplied with 60. So this is equal to 210 multiplied with 6 divided by 75.33 into 60. After solving this, we are getting COP of refrigeration system as 0.279. Okay. Now last point is power supply to the blower. Okay. So power supply to the blower, we are getting directly from the formula, because this power is getting blower is required to taking the air, suck the air from the heat exchanger, ram air, that is a ram air, and for that power is delivered from the whatever power we are generating during the expansion of the air during the turbine process. Okay. So so that's why this will be same power, so we'll get PB is equal to m dot a multiply with Cp in bracket T5 minus T4. So T5 is the cabin temperature minus T4 as the sorry, this is the point number 3 minus T4. So expansion process. So you will substitute the values, and after we are getting power delivered to the blower is equal to MACP multiplied with T3 minus T4 divided by 60. So after substituting values, so power delivered to the blower as PV is equal to 1.004, as the CP mass flow of air is 23.5 in bracket 341, T3 temperature minus T4 temperature 246.6 divided by 60. After solving, we are getting the power delivered to the blower PB is equal to 37.24 kilowatt. Okay, so thank you.